Welcome back to the video. In this video, we'll be going through a question from astronomy. So let's start. So Procyon is the brightest star in the constellation Canis Minor. The graph shows how the radiated intensity from the Procyon varies with wavelength. So this is a graph of a black body radiator, and we assume that all stars are black body radiators, so we can plot the black body radiation curves for them and then use that to find the properties of stars such as stellar radius, temperature, and etc. Now it says a website states that Procyon has twice the diameter of the Sun. Assess the accuracy of this statement, and they've given you the luminosity of Procyon and the diameter. So first thing what I'm going to do is I'm going to tell you guys the formula that you need to use. So we have these two formulas that are already linked with this topic. So first is Wien's law and the second is Stefan-Boltzmann law. Okay, so these two laws, and I've given the constant values as well. You can find this in your data booklet. Okay, so what you want to do here is we're going to find lambda max first. So we're going to find lambda max from the graph, and using that we're going to find the value of t, and that's equal to the constant w. So first thing I want to do is I'm going to find this value of t. Now using that value of t, I'm going to plug it into the formula. L is equals to sigma 4 pi r square, which is the surface area of a sphere, t to the power 4. So I'm going to know temperature already. I know the luminosity, and all I have to find now is the radius. And then I'm going to find the radius, times it by 2. I'm going to get the diameter, and then I'm going to compare it with the diameter of the Sun. So I'm going to compare it, and then I'm going to get my final statement as the final mark. Statement. So that's the operation that we're going to go and do. So let's see the graph first. Now, remember, this lambda max doesn't mean that the lambda is maximum. It means the lambda value at which the intensity is maximum. Okay, so we're going to see where the intensity is maximum. It's right over here. It's going to be right around here, and then we're going to get this. Okay, be careful of the units. It's nanometers, so there's going to be 450 nanometers. Okay, so it's going to be 450 nanometers. So we're going to plug it in, 450 times 10 to the raised power of minus 9, and then temperature is equals to, this value is 2.898 times 10 to the raised power of, it should be minus 3, and that gives me a temperature value of 6,440 Kelvin. Now I'm going to plug that into the formula. I already know the luminosity, now they've given me the luminosity right over here. So 2.65 times 10 to the raised power of 27 is going to be equals to, what's going to be the sigma 5.67 times 10 to the raised power of 8, 4 pi, and the radius square, and then 6440 to the power of 4. Now what I'm going to do is I'm going to find the value of r. I wrote it as 8 is minus 8, my bad. 7 times 10 to the power of minus 8. So that's giving me that's giving me 1.47 times 10 to the raised power of 9 meters. Okay, that's the answer. So we took the luminosity, we moved the Stefan-Boltzmann constant. I forgot to take this as minus 8, by the way. And then 4 pi, and then this, and then we take it all to the other side, and then we're going to square root it to find the value of r. Right, now what I'm going to do is I'm going to times it by 2. And what is the statement? It says that Procyon has twice the diameter of the Sun. Okay, I'm going to times this by 2. Let's times it by 2. And I'm getting a value of 2.94 times 10 to the raised power of 9 meters as the diameter. So let's divide by the diameter of Sun. Diameter of Procyon, so this is the diameter now. This is the diameter. Divide by the diameter of the Sun. So let's see what we get. Okay, so we're getting a value of 4.22, which means the diameter of Procyon is actually 4 times more. And 4 is greater than 2, so the statement is not accurate. The statement says twice, but it's actually 4 times more than the diameter of the Sun. So that's the answer to this question. So we have another question, and this says the image shown is a representation of our galaxy, the Milky Way. Astronomers think that there is very large concentration of stars in the central region of the galaxy. Outside the central region, the concentration of stars is very much less. All stars in the galaxy are rotating about its center. It can be shown that the velocity of a star at a distance r from the center of the galaxy is given by this formula. So we're familiar with this formula already. This is the formula you get when you equate the centripetal force is equals to the gravitational force. You're going to get mv squared over r is equals to g mm over r squared. And then you can cancel this out, and then this cancels out. So you get the formula from there. Okay, then it says, the graph shows how astronomers expect v to vary with the distance r. Explain how this expression gives the variation of v with r shown in the graph. So now we can see something happening here. We can see that initially the radius is increasing and the velocity is increasing with it. So the radius is increasing, the velocity is increasing, okay, that's how that works. And then we see after a certain point, the radius increases but the velocity decreases. So we know that v squared is equals to gm over r. If the, what am I saying? So as we were discussing the question, we saw that we have the distance r, the velocity v here, and then goes like this. This is the curve, okay? Now, what we saw here was that, notice something. Let me change the color. Let's pick a bit more darker color. Let's go with this color. Okay. Now, I want you to notice something. We know that v is equals to square root gm over r. And if we square both sides, we'll get v squared is equals to gm over r. Now, what should happen actually is as r increases, the v should decrease. Okay? The first thing I want you to see that, okay? That if r is increasing, v should decrease. But notice this region here is not following that pattern. But then this region here follows that pattern. So what could possibly happen that could cause the velocity to increase here? Now we know our g here will remain constant, so we can ignore that. We can talk about mass. Mass increases a lot. So we can say the mass increases a lot, or we can write at a higher rate, so the velocity increases. For this is quite simple. They have given it to you in the question. Let me show you. Astronomers think there's a very large concentration of stars in the central region of the galaxy. Outside the central region, the concentration of stars is much less. So what's happening here is, remember in our formula, v is equals to v squared is equals to gm over r. This m is the mass. So let's say if something is orbiting here, we're seeing the mass of everything that's here, right? And if we're orbiting here, we're seeing the mass of everything that's in all of this region, in this circle. Okay? So essentially what's happening is as you go from here to here, the mass is going to increase, right? As you go from here to here, your mass is going to increase because the region you're covering in your orbit is increasing. So at first we're covering this region, and then we're covering this region. So you can notice that this mass will be less and this mass will be much more. But when we go from here to here, the mass that's in all of this region is not a lot. It's very less. So there's little to no change in the mass when you get to this specific area. But until this, the mass will increase a lot. So that's kind of the logic or the understanding or the rationale behind what we're doing. Now, I've written a very good answer here for you to understand. Mass will increase at a high rate. So even though our r is increasing, so that's going to happen when you're here, when you're moving here. Okay, mass will increase by a lot at a high rate, and then even though your distance is increasing, the orbital velocity still increases. Now, as the distance is increasing, the v will reach a peak and then go down. And then the mass will approximately remain constant because there's barely any mass around here. So that's kind of the explanation of it. And yeah, so let's move forward to the next question. So we have already seen these graphs. If you have seen the lecture video, we saw the same graph for the sun. So if you haven't checked it out, please do check it out. And this graph is a bit different because it's in a different situation, but it's the same logic. We're going to be talking about, now if you see this and you're thinking dark matter, then yeah, you're right. So we're going to talk about dark matter, right? So as soon as I say observed and expected and all of that information above as well, it's all hinting, and it's going to talk about dark matter at the end. So here it says observed variation of V and with R has been added to produce the graph below. And it says, here is the observed and here is expected, the one where we tried to understand the previous part. And the real one is this actually. So we have to explain why the observed varies as shown. Well, that's simply because of dark matter. So the answer for this is quite simple. There's dark matter which we cannot see because it has no photonic interaction. It cannot interact with light basically. And this dark matter has mass, right? So this dark matter has mass, and because of that mass, our V will not change as much as we expect it to change. It's not going to go down as much because this mass is present, and because of that, the V doesn't decrease too much. The velocity isn't going to decrease a lot like we expect it to. And this mass is spread throughout the galaxy. Okay? So that's going to give you the 2 marks right there. Let's move on to the next question now. So here we have the next question. This is also done in the playlist videos. The ultimate fate of the universe may be a closed universe, but astronomers cannot be sure what their current models predict. Now, it says why astronomers cannot be sure. It's because, like we saw, we don't know the mass of the universe. We have uncertain about the mass of the universe, right? Because if we want to see the density of the universe, we need the density of the universe is equal to the mass over the volume. And if we don't know the mass, we cannot find the density of the universe. So we're uncertain about the mass of the universe. And this is because we are not sure about the amount, or rather, we're not sure about the mass of dark matter. Okay, and the next thing that you want to write, another important point, is that for the universe to be closed, the critical density and the density of the universe has to be greater than the critical density. So that's going to give you 2 marks right there. I have the examiner report as well for all the questions. Here it says most candidates correctly read the wavelength value and from the graph and used this in Wien's law, where rarely the maximum value of the wavelength axis was used, but 450 was the most common wavelength value seen. There were some occasional calculation errors. So basically this question, if you read the rest of it as well, was pretty easy and most people were able to do it well and score some marks. But the real problem came in this other question that we did, question number 16. This is all from the, I think, Jan 2022 or 2021 paper, I'm not sure, but it's from that paper. And it says that this question was very poorly understood by most of the candidates. And it says most responses, so most of the people, they didn't understand, and they just simply described the graph rather than explain what's happening. And yeah, so this question was poorly understood, and most of the students, they didn't know how to handle the thing about the mass changing. That the mass initially was increasing and then the mass was equals to constant. So that's what students struggled with, and most of them just explained the graph rather than trying to explain what's happening. Why is the graph changing in that way? So make sure when they tell you to explain something, when you're told to explain something and they've given you some stuff, some graph or something, you don't just state what's given. You state what's given and then explain why it's given like that. Why, if they're giving you a graph that goes something like this, you tell, okay, the graph reaches a peak, then goes down. Why does the graph reach a peak? Why does it go down? Explain that. Okay, that's what's important when you do these type of questions, especially the explain one. They always tend to have a strict marking scheme, and you need to have a really good concept. Now here is the next question, and it says dark matter was often identified, and it says some students were trying to explain it in terms of dark energy, but that's a different concept. So that's different. And some students even refer to Doppler effect. Now these concepts are completely different. Remember when we're talking about mass, there's mass changes in the galaxies that we don't expect. It's because of dark matter. Okay, that's an important point as well. Now the last part is also answered the same way, that some candidates were able to answer it. Some connected it to topics that were outside of the scope of the question, such as redshift and Hubble's constant, but those obviously aren't connected to this. So make sure you talk about the relevant things in the question. And yeah, I think we'll end the video here.